Hello and welcome to this week's lesson. We're talking about the Laplace transform. We're going to cover two sections. Section 4.3 is going to be a revision of the ideas from 2 weeks ago, and then the main topic for this week's lesson is step functions. 2 weeks ago, I showed you how to use the Laplace transform to solve some initial value problems. We're going to do a little bit of revision, a little more examples. To solve a differential equation with the Laplace transform, the key formulae are that the Laplace transform of the derivative of f is s multiplied by the Laplace transform of f minus the initial condition of f0, and then similar f or n derivatives of f. Example. Suppose you are asked to use the Laplace transform to solve this initial value problem. First thing we do is we take the differential equation and we take the Laplace transform of the differential equation. We have the Laplace transform of y double prime minus 3 times the Laplace transform of y prime plus 2 times the Laplace transform of y is equal to the Laplace transform of cos t. Using the formulae from the previous page, the Laplace transform of y double prime is this term in green, s squared capital Y minus sy0 minus y prime of y0. The Laplace transform of y prime is sy minus y0. The Laplace transform of small y we write as capital Y. And if we look at our table of Laplace transforms, we can see that the Laplace transform of cos t is s over s squared plus 1. Then we use the initial conditions. Y of 0 is equal to 0, so we can cross out this term and we can cross out this term. Y prime of 0 is also 0, so we can cross out this term. On the left side, we have s squared minus 3s plus 2 capital Y is equal to s over s squared plus 1. Divide both sides by s squared minus 3s plus 2. We get capital Y is s divided by s squared plus 1, s squared minus 3s plus 2. Or if we factorize this, s over s squared plus 1, s minus 2, s minus 3. We need to find the inverse Laplace transform of capital Y. In other words, we need to find the inverse Laplace transform of this function. For a function like this, we use partial fractions. This is going to be something over s squared plus 1 plus something over s minus 2 plus something over s minus 3. S minus 2 and s minus 3 are first degree polynomials, so on top we have a 0 degree polynomial. S squared plus 1 is a second degree polynomial, so on the top we have some first degree polynomial. We can multiply this out, put this all over the same denominator, and then we can find capital A, capital B, capital C, and capital D. I'm going to leave it for you to check that A is 1 over 10, B is equal to minus 3 over 10, C is equal to 2 over 5, and D is equal to minus a half. So we have 1 over 10s minus 3 over 10 over s squared plus 1 plus 2 over 5 over s minus 2 minus a half over s minus 1. Which we can write like this. 1 over 10 multiplied by s over s squared plus 1. We do this because s over s squared plus 1 is on the table of Laplace transforms. Minus 3 over 10, 1 over s squared plus 1, plus 2 over 5, 1 over s minus 2, minus a half, 1 over s minus 1. Using our table of Laplace transforms, we can look up s over s squared plus 1, and we see that's the Laplace transform of cos t. We can see that 1 over s squared plus 1 is the Laplace transform of sine t. 1 over s minus 2 is the Laplace transform of e to the power 2t. And 1 over s minus 1 is the Laplace transform of e to the power t. As soon as we've done this, as soon as we know capital Y is a linear combination of Laplace transforms of functions, we can write down the solution to the initial value problem. Small y is the inverse Laplace transform of capital Y, which of course must be 1 over 10 cos t minus 3 over 10 sine t plus 2 over 5 e to the 2t minus a half e to the power t. And I can show you the graph of this function, which looks like this. One more example. Use the Laplace transform to solve this problem. Of course, we could solve this using the ideas from chapter 3, using the method of undetermined coefficients, etc. But I want to solve this problem using the Laplace transform. So what I do is I take the differential equation, y double prime plus 2y prime plus y is equal to 4 e to the power minus t. And I'm going to put the Laplace transform on everything. The Laplace transform of 4e to the power minus t is 4 over s plus 1. Next, I'm going to do the Laplace transform of y prime. That's s capital Y minus y0. We can do the Laplace transform of y double prime. That's s squared capital Y minus s y0 minus y prime 0. And then we use the initial conditions. Y of 0 is equal to 2. We have a 2 just here and a 2 just here. Y prime of 0 is minus 1, so minus y prime of 0. This is all going to be plus 1. There we go. Now let's rearrange to find capital Y. On the left side, we have s squared plus 2s plus 1 multiplied by capital Y, and then the extra terms, minus 2s plus 1 minus 4, which we can move over to the right side. I also want to factorize s squared plus 2s plus 1, and I want to put the whole of the right side over the same denominator. Factorizing this, we get s plus 1 all squared, and then the right side I'm going to put over the same denominator. It becomes 2s squared plus 5s plus 7 divided by s plus 1, which you can check later. And then finally, I want to divide both sides by s squared plus 1 squared. You will get s plus 1 cubed over here and nothing on the left. Right, we want to find the inverse Laplace transform of this function. The inverse Laplace transform of 2s squared plus 5s plus 7 divided by s plus 1 cubed. Again, for a function like this, we need to use partial fractions. And I'm going to leave it for you to check that if we write this as a over s plus 1 plus b over s plus 1 squared plus c over s plus 1 cubed, then we get a is 2, b is 1, and c is 4. For the time being, just assume that I'm correct on this, but please check it later. So our function is 2 over s plus 1 plus 1 over s plus 1 squared plus 4 over s plus 1 cubed. We want to find the inverse Laplace transform of this function. And I choose to break it up like this. 2 multiplied by 1 over s plus 1, because 1 over s plus 1 is on the table of Laplace transforms. 1 over s plus 1 squared should also be there. And 4 over s plus 1 cubed is not on the table of Laplace transforms. 1 divided by s plus 1 cubed is not on the table of Laplace transforms, but 2 over s plus 1 cubed is on the table. So I take one factor of 2 out and I leave one factor in. From our table of Laplace transforms, you can see that the Laplace transform of e to the power minus t is 1 over s plus 1. That's this one. The Laplace transform of t multiplied by e to the power minus t is 1 over s plus 1 squared. And the Laplace transform of t squared e to the power minus t is 2 divided by s plus 1 cubed. Now that we know this, we can write down the solution. The solution to the initial value problem, once we've put these formulae in and simplified, you can check is 2t squared plus t plus 2 multiplied by e to the power minus t. And I can show you that the graph looks like this. I'm going to take a And now I'm going to continue. The previous section should be revision. It was the ideas we talked about 2 weeks ago. The main topic for this week's lesson is the idea of step functions. The unit step function, a function we're going to be using a lot in this week's lesson, which we can call u subscript c, is a function which is defined on the non-negative real numbers, and it's defined to be equal to 0 if t is strictly less than c, and the function is equal to 1 if t is greater than or equal to c. Graph of the function is here. Basically, it's just a graph which is 0 until we get to c, and then it jumps up and is equal to 1 for all of the way between c and infinity. First example, draw the graph of y is equal to 1 minus uc of t. The graph of uc from the previous page, it was 0, and then it jumped up and it was equal to 1. If we do 1 minus this, 1 minus 0 is 1, 1 minus 1 is 0. So instead, we just have the function which is 1 between 0 and c, and then it jumps down and it's equal to 0 all of the way from c to infinity. Another one, draw the graph of y is equal to u1 of t minus u2 of t. Now, clearly, the first thing we can notice is the numbers 1 and the number 2 are important numbers. u1 of t changes between 0 and 1 at 1. u2 of t changes between 0 and 1 at 2. So clearly 1 and 2 are going to be important numbers. So we're going to consider this function on 3 different intervals. between 0 and 1, between 1 and 2, and between 2 and infinity. Here we go. Between 0 and 1, between 1 and 2, or between 2 and infinity, we are looking at u1 minus u2. Clear this up a little bit. First, let's look at u1. Here we go. The function u1 is equal to 0 between 0 and 1. So we should have a 0 just here. Between 1 and 2, the function is equal to 1. So we should have a number 1 just here. And between 2 and infinity, the function is also equal to 1. So we should have 0, 1, 1 just here. Next, I want to look at u2. Again, the graph is at the top. First of all, between 0 and 1, the function is 0. We should have a 0 just here. Between 1 and 2, the function is also 0. So again, a 0 just here. And then between 2 and infinity, the function is equal to 1. So we should have 0, 0, 1 here. Between 0 and 1, the function is 0 minus 0, or 0. Between 1 and 2, the function is 1 minus 0, or 1. Between 2 and infinity, the function is equal to 1 minus 1, or 0. So the function is 0, and then 1, and then 0, which looks like this. Next example. Write this function in terms of the unit step function. We have a function which is 2 between 0 and 4, then it's equal to 5 between 4 and 7, it's equal to minus 1 between 7 and 9, and it's equal to 1 between 9 and infinity. We can draw the graph like this. First, I want to look at the first piece of the function. The function starts with 2. First part of the function is equal to 2. So we expect our function to be 2 plus something. Then when we get to 4, it jumps up 3. It goes from 2 to 5, so it's going up 3. And this is because this is happening at 4, we expect our function to be 2 plus 3 u4. And then for the rest of the function, plus something. Remember, u4 is equal to 0 between 0 and 4. So on the first part of the function, we have 2 plus 0. And then u4 is equal to 1 after 4. So after 4, we have 2 plus 3, or 5. Next, I want to look at the part of the function between 7 and 9. What happens at 7? At 7, we go from 5 to minus 1. So at 7, we go down 6. So we would expect to have minus 6 u7 in our function. At 7, we go down 6, so minus 6 u7. And then for the last part of the function, we still have plus something. The next change happened at 9. At 9, we go from minus 1 to 1. We're going up 2. So we expect our function to finish with plus 2 u9. The answer to this question is 2 plus 3 u4 minus 6 u7 plus 2 u9. Next example. Write this function in terms of the unit step function. Again, we have a function which is defined in 4 different pieces, but these are the first 3 pieces are not horizontal lines, instead these are diagonal lines. Here's the function. The function starts with f of t equal to t. Then the function changes when t is equal to 1, when t is equal to 2, and t is equal to 3. So we're expecting the function to look like this. At the start, we have f of t is equal to t. Yeah. There's some change happening at u1. So it's going to be something multiplied by u1. Then there's a change happening at u2. So it's going to be something multiplied by u2. And then there's another change in the function happening at u3, 3. So we expect to have plus something u3. At each one of these changes, at each one of these jumps, we're going to calculate a function on the right minus function on the left. In the previous example, for example, we went from 2 to 5. I said we go up 3 because 3 is a function on the right, which is 5, minus the function on the left, which is 2. We'll do the same thing here, but with functions instead of numbers. So, first of all, at the first jump, the function on the right is t minus 1, and the function on the left is t. So at the first jump, it's t minus 1 minus t. At the second jump, the function on the right is t minus 2, the function on the left is t minus 1. So at the second jump, it's going to be t minus 2 minus t minus 1. And these are numbers because the shape of the function, the slope of the function is the same on each side. We're just shifting downwards. At the third jump, we're not just shifting downwards because the function is changing. We go from a function of slope 1 to a function of slope 0. So this one's not going to be just a number. At the third jump, we do function on the right minus function on the left. So 0 minus t minus 2 or 2 minus t. Then we're ready to put these into the formula. We can write this function as t minus u1 minus u2 plus t minus t u3. And another example. Write this function in terms of the unit step function. T squared and then 4 and then 4e to the power t minus 3. Here's a graph of this function. This function is not discontinuous, this function is continuous. I've chosen the numbers so that these 3 parts of the function match up neatly. But still, the function is changing at 2 and the function is changing at 3. So we have the same idea with these jumps. Jumps as in change of function. We start with t squared, so the formula would start with t squared, plus something at u2, because there's a change at 2, plus something at u3, because there's a change at 3. For the first jump, we do function on the right minus function on the left. The first jump, we do 4 minus t squared. For the second jump, again, function on the right minus function on the left. So for the second jump, we do 4e to the power t minus 3. I said a mistake, minus 4. This is a typo here. This should be e to the power 3 minus t. Okay, so that's the step function, but we're talking about the step function in this chapter about the Laplace transform. So the question we should ask immediately is, what is the Laplace transform of the unit step function? I've put the formula at the top. Let me remind you, the Laplace transform of f is the integral from 0 to infinity, e to the power minus st f of t dt. Using this formula, we can calculate the Laplace transform of the unit step function. We're doing the integral from 0 to infinity, e to the power minus st, uc dt. And remember, this unit step function is equal to either 0 or 1. First, the function is equal to 0, and then the function is equal to 1. So between 0 and c, we have a 0 in our integrand. Between c and infinity, we have a 1 in our integrand. And of course, we don't need to integrate 0 because the integral of 0 is 0. So really, we're calculating the integral from c to infinity of e to the power minus st dt. And we know how to do this. This is e to the power minus cs divided by s. This is an important formula, so let's write this as a theorem, and you will find this on your table of Laplace transforms. The Laplace transform of uc is e to the power minus cs divided by s. We're going to be using this formula a lot this lesson, and also next lesson we're going to be using this formula. Next idea. Let's suppose we have some function, just any function. I've drawn it like this, but just think of any function that you could draw, any squiggly line. And what I want to do is I want to take this function and I want to shift it to the right, like this. More precisely, I'm going to define a new function called g. G is going to be the same as the function f, shifted to the right, if t is greater than c, and the function is going to be equal to 0 between 0 and c. We can write a function like this in terms of the unit step function, using the same ideas as we did before. The function starts at 0, so it's going to be 0 plus something. There's a jump at c, so it's going to be 0 plus something uc, and the jump is function on the right minus function on the left. The jump is f of t minus c. We can write this new function as uc multiplied by f at t minus c. And then we might ask, okay, what is the Laplace transform of g? Let's calculate it. Again, we have our formula for the Laplace transform. The integral from 0 to infinity, e to the power minus st, uct multiplied by f of t minus c. And the unit step function is equal to either 0 or 1. Between 0 and c, the function is 0, so we don't need that. And then between c and infinity, the function is equal to 1. So really, we're just doing the integral from c to infinity of e to the minus st f at t minus c. To calculate this, we can do a substitution. We can substitute in a new variable, u is equal to t minus c. Then, of course, du is equal to dt. So instead of dt, we can just write du. T is equal to c is the same as writing u is equal to 0. Instead of c just here, we're going to have 0. Do this substitution. We have the integral from 0 to infinity now. E to the power minus s, and then instead of t, we have u plus c. F of u du. We can take a factor of e to the power minus sc outside the integral. I just lost connection. I hope you can hear me now. We can take a fact of e to the power minus cs outside the integral, and then we have the integral from 0 to infinity, e to the power minus su f of u. But of course, this is just the Laplace transform of f. So we have that the Laplace transform of g is e to the power minus cs, Laplace transform of f. This is an important theorem, so again, this is an important formula, so again, let's write this as a theorem. The Laplace transform of uc, f at t minus c, is e to the power minus cs, f of s. We're going to be using this formula a lot this week and next week. Next example. Find the Laplace transform of f of t is equal to t, t minus 1, t minus 2, and then 0. This is the function that we looked at earlier. We already know a way to write this function in terms of the unit step function. We saw earlier that this is the same as t minus u1 minus u2 plus 2 minus t u3. Now, we need to do something before we can go on. The formula in the previous page had uc here and f of t minus c. And these were the same number, but we don't have the same number just here. We have the number 2 and we have the number 3. So we're going to have to make a small change first of all. We have to write the function like this. T minus u1 minus u2, that's the same as before. And then minus u3 t minus 3. And this is the form we want because now we have the same number here, number 3 and the number 3. So now we can use the formula at the top of the page. Capital F, the Laplace transform of small f, is the Laplace transform of t minus the Laplace transform of u1 minus the Laplace transform of u2 minus the Laplace transform of u3 minus the Laplace transform of u3 t minus 3. And the first 4 are easy. We can just look these up on the table of Laplace transforms. For the final one, we use the formula at the top to see that we have e to the power minus 3s multiplied by the Laplace transform of t. But of course, the Laplace transform of t is just 1 over s squared. So we go e to the minus 3s multiplied by 1 over s squared. Find the Laplace transform of this function, which is equal to sine t if t is between 0 and pi over 4, or sine t plus cos t minus pi over 4 between pi over 4 and infinity. The first thing to notice is we can write f as sine t plus gt, where gt is equal to u pi over 4 cos t minus pi over 4. Hence, capital F is the Laplace transform of sine t plus the Laplace transform of u pi over 4 cos t minus pi over 4. And again, we have the same number here. We have pi over 4 and pi over 4. So we can use the formula at the top. And we can see that this Laplace transform is equal to e to the power minus pi over 4s multiplied by the Laplace transform of cos. The Laplace transform of sine and the Laplace transform of cos we can find on our table. We can put these in and we have 1 over s squared plus 1 plus e to the power minus pi s over 4 multiplied by s over s squared plus 1. We could do some inverse Laplace transforms as well. Find the inverse Laplace transform of 1 minus e to the power minus 2s over s squared. And the calculation goes like this. Small f, the inverse Laplace transform of capital F, is the inverse Laplace transform of 1 over s squared minus the inverse Laplace transform of e to the power minus 2s over s squared. The first one is straightforward. The inverse Laplace transform of 1 over s squared is just t. And then we use our shift formula to see that we then have 2 multiplied by t minus 2. Or we could write this as the function which is equal to t between 0 and 2, and then equal to 2 between 2 and infinity. Another formula we're going to need. What is the Laplace transform of e to the power ct multiplied by f of t? We can calculate this out, and we find that this is the same as capital F of s minus c, where capital F is the Laplace transform of small f. Again, we can write this as a theorem because this is an important formula. This is a formula which you will find on your table of Laplace transforms. For example, find the inverse Laplace transform of 1 over s squared minus 4s plus 5. Now, first of all, note that we can complete the square on the denominator, and we can write this as 1 over s minus 2 squared plus 1. If capital F is 1 over s squared plus 1, then we have that capital G is capital F of s minus 2. Which is great because we have this in our formula. We can use the formula at the top to see that because the inverse Laplace transform of capital F is sine t, the inverse Laplace transform of capital G is the inverse Laplace transform of f of s minus 2. That's e to the power 2t multiplied by the inverse Laplace transform of f, or e to the 2t sine t. Now, you will note that when we're trying to find the inverse Laplace transform of a rational function like this, I've shown you 2 different methods this lesson. When do we use each lesson? When do we use each method? Ask the question, does the denominator have roots in R? If the answer is yes, we factorize and then we use partial fractions. If the answer is no, then we complete the square and then we use this formula for the Laplace transform of e to the power ct. F of t is capital F of s minus c. For example, find the inverse Laplace transform of 30s plus 440 divided by s squared plus 32s plus 240. First thing to note is the denominator has 2 real roots, minus 12 and minus 20. So we can use partial fractions. You can check that capital G is 10 divided by s plus 12 plus 20 divided by s plus 20. And this number, 10, 12, 20, 20, hopefully looks familiar to you. I'm going to leave this example for you to finish. Find the inverse Laplace transform of 10s plus 12 divided by s squared plus 40s plus 420. Because the denominator has complex roots, we're not going to use partial fractions. Instead, we're going to complete the square. And I'm going to leave it for you to check that capital G is 10s plus 12 over s plus 20 squared plus 20. And again, look, 10, 12, 20, 20, that's today's date. Now that we've completed our square, we can calculate the inverse Laplace transform. And I'm choosing to break capital G up like this. 10 multiplied by this function, but plus 12 divided by 20 multiplied by this function. Why did I do 12 divided by 20 outside and 20 inside? So that we end up with a function on the table of Laplace transforms. Now, if we say that capital F is s over s squared plus 20, and capital H is 20 divided by s squared plus 20, then we have that capital G is 10f at s plus 20 plus 12 over 20 capital H at s plus 20. And we can find the inverse Laplace transform of capital F and capital H on our table of elementary Laplace transforms. We have cos root 20t and sine root 20t, and that's all we need. Therefore, small g, the inverse Laplace transform of capital G, is 10 multiplied by the inverse Laplace transform of capital F of s plus 20, plus 12 over 20, inverse Laplace transform of capital H of s plus 20. First, I'm going to use the left formula to write this as 10 e to the power minus 20, inverse Laplace transform of capital F, plus 12 over 20, e to the power minus 20t, inverse Laplace transform of capital H, and then put these formula in. 10 e to the power minus 20t cos root 20t plus 12 over 20 e to the power minus 20t sine root 20t, which is the end of this week's lesson. Next week will be our third and final lesson about the Laplace transform. We're going to cover differential equations with discontinuous forcing functions, which is perhaps the most relevant section for engineers who want to use the Laplace transform. And then we will finish by talking about the convolution integral. If you have any questions, you can ask them in chat. Let me answer the first question, which I'm guessing will be asked. No, I haven't started marking the exams yet. It will be another week or two before you get your results.